So for this video, we're going to focus on 3 examples how to find the domain of a given function. Now, finding the domain of a function really depends on the type of function that you are given. So taking a look at the example that we have here in front of us, the first 2 things that I notice is we have a radical expression right over here, right? We have our square root portion here. And then if I look at the backside over here of this function, I also have a rational function. What that tells me, so typically when it comes to domains of most functions tend to be negative infinity to positive infinity, except for some certain stipulations. If you have a radical in the function, your radicand, what's underneath of it, needs to be greater than or equal to 0. If you have a rational function, so anything in fraction form, what's going to throw a domain off of something like that is when the denominator is equal to 0. Keep in mind when the denominator is equal to 0, it's undefined, so we want to figure out what would make that denominator equal 0. So that's kind of what we're working with this example. We're working with rules of radicals and rules of rational functions. So we have 2 stipulations in this problem that we need to focus on. The first stipulation, we need to figure out when the radicand here, the 12 minus x, is greater than or equal to 0. So just drop down what's underneath of that, set it greater than or equal to 0, and solve this situation here. So we can subtract 12 from each side to get negative x is greater than or equal to negative 12. Divide out your negative 1 on each side. Drop down x. Keep in mind, when you're dealing with inequalities, when you multiply or divide by a negative like we are here, you must flip the inequality symbol. Otherwise, the right-hand side, we're going to drop down that positive 12 right over there. So far, our domain has to be less than or equal to a positive 12. But our second restriction over here, rules of rational functions say you need to set your denominator equal to 0 and solve. Your solutions are restricted values. So when we solve this little mini equation here, it's one step. Add 8 to the other side, we get x is equal to 8. That means 8 cannot be part of our domain. So when we take a look at our first restriction here, x is less than or equal to a 12. So here's our 12. It can equal 12 and it can be everything less than 12 is what we're currently looking at. But we also have the restriction where x cannot be 8. So let's say 8 is about here. What that tells us, so think of it like we have a hole right here at this value. We do not want our function to equal 8, but everything else around it is fine. So this is what the domain of our function currently looks like. Domain always needs to be written in interval notation. So if we write this up in interval notation on the left-hand side here, negative infinity, and it's going to be negative infinity up until this 8 right over here. Again, open dot, you're always going to have a parentheses on that. We're going to pick up our domain on the other side of 8 here, and then it's going to run until we get to this 12. Since 12 is our only solid dot here that we're working with, we will have a bracket on that 12. Again, open dots always have parentheses, infinities always have parentheses. Otherwise, this would be the domain of this function. Our next example, we have log base 4 of x squared minus 3x minus 10. So what we need to remember when we're finding the domain of a logarithmic function is you want to take a look at this piece right over here. You're always going to have log base something of some kind of term right over here. It might be one thing, might be multiple terms, but whatever this is falls in this position right over here, kind of like our x spot. What we want to do is we want to take that, our x squared minus 3x minus 10, and you want to set it greater than 0, and you want to solve that. Now, because we have a quadratic equation here, right? We have our quadratic equation that we are setting greater than 0 that we need to solve. Rules of solving quadratic inequalities. We need to try and factor this left-hand side here. So we're going to factor this trinomial here, which x squared tells us x times x. Factors of 10 that add or subtract to get us a 3 here is going to be our 2 and our 5. If the back number is negative, we know different signs. Middle term, the sign of the middle term will always go with the bigger number. So that minus is going to go with the 5. The plus is going to go with the 2. Now, typically we would take a look at these two here, and typically our next step would be to split these up, set them each equal to 0, and solve, which would give us the values -2 and a +5. Now what we're going to do here, So the solutions that we get when we work this, when we work a quadratic inequality here, the solutions we get are called boundary points here. So we're going to put those two numbers on our line graph here. And what we need to do here is we need to test our intervals. Our domain is going to be some of these intervals here. So essentially when we plug these two numbers up here on our line graph here, it creates three sections, right? The left section, the middle section, the right section. We need to figure out which is the right sections to shade here. So what I tend to do is I tend to choose whatever interval here has 0 in it, which is going to be my middle section. Plug it into your inequality here. If we plug it into our inequality, 0 squared minus 3 times 0 minus 10. Right, if we plug in 0 for x, well, that's 0, and we're left with negative 10 is equal to 0. That means this middle section here is not going to work since negative 10 is not greater than 0. All right, so that means 0 that's in the middle interval is not working, which tells us we are going to shade the other two sides. When it comes to these examples, you're typically always either shading in the middle or you're shading on the outside. But again, we can use the math to verify this. Like we can plug in a negative 3 here, and if we plug in a negative 3, we should see that this does work out. We are left with a 9 plus a 9 minus a 10. 18 minus 10 is still an 8. And 8 is definitely greater than 0. And we'll see that the same thing is true like if we plug in a 6. You have 6 squared minus the 3 times a 6 minus a 10. Is this greater than 0? 6 squared is 36 minus an 18 minus a 10. That gives us 36 minus a 28, which is an 8. And 8 is definitely still greater than 0. All right, so our domain for this given function here, negative infinity to negative 2, union 5 over here to positive infinity. All right. And for our third example, we're going to find the domain of the following function here. So when I look at this function, I'm seeing that we have a radical within a radical. Rules of working with radicals say that you want to set the radicand greater than or equal to 0 and solve. Now because we have two radicals, we're going to be doing this twice. We have the radical of the square root of x plus 7. We also have the radical square root of 2 minus the square root of x plus 7. We want to solve both of these when they are positive, right? We don't want any negative numbers underneath our square root symbol. We want them to be positive. 0 is okay. So we're going to set them greater than or equal to 0, and we are going to solve. Now, typically we would just start by squaring each side here, or really you can just take the radicand, and set it equal to 0 and solve, which would just look like the x plus 7 is greater than or equal to 0 would be a good starting point. Otherwise, just subtract the 7 on each side, and x is greater than or equal to a negative 7. Over here, again, clearing out our radicals. Again, we can square each side to get 2 minus the square root of x plus 7 is greater than or equal to 0. Subtract that 2 on each side. And then go ahead and divide out the negative right over here so that we're looking at the square root of x plus 7. Well, rules of inequality say when you multiply or divide by a negative, you do need to remember to flip the inequality symbol. Otherwise, we do get a positive 2 on this side. Squaring each side, we are left here with an x plus 7 is less than or equal to a 4. And when we subtract 7 on each side, x is less than or equal to a negative 3. So if we take a look at what that gives us here, we have a negative 7. We also have a negative 3. They can equal these numbers here as well. We want it greater than negative 7, but we want it less than negative 3. So we want this interval right over here. So we are looking at our domain of being negative 7 to our negative 3.